So today we're going to start off by talking about solving quadratic equations. So if I have an equation, how do I know it's a quadratic equation? It has a squared term, right? And all quadratics can be written in their general form, right? General form of a quadratic is ax squared plus bx plus c equals 0, right? If we get everything on one side of the equation and we fully simplify it down, we're always going to have an equation, if it is a quadratic equation, that looks like that. Ax squared plus bx plus c. The ax squared is what we call the quadratic term, of course. That's what it gives the equation its name. The bx term, we're going to refer to that as the linear term. And then, of course, the c is the constant term. It has no variable associated with it, so it does not change depending on what x is. So that's the general form of a quadratic equation. And so an example of a quadratic equation might be something like x squared minus 20 is equal to x. Now, the thing about quadratic equations is they don't always end up in general form right away, nice and neatly like we see, in the red up top there. It might look something like this, where you just have an equation, and you're going to identify that it's a quadratic and not a linear equation by the fact that that's an x squared term there. Now, you're all familiar with quadratic equations from Algebra 1 and Algebra 2, and so what's the difference in our approach between like a linear equation, where we're just trying to isolate the variable, and a quadratic? What do we have to do to solve a quadratic? That's the first step. No matter what method we're going to use, we definitely want to do that. So we got to put all the terms on one side. That means, well, which side do we generally want to put it on? Yeah, we want to put it in general form essentially. If the quadratic equation is in general form, it's going to make it a lot easier to solve. And so in general form, generally we want a to be positive, which means we want to put it on the side of the equation that makes the x squared term positive, right? So that would be the left side in this case. So to accomplish that, let's go ahead and subtract the x from both sides. Right, so now we put it in a general form. Now, can you guys remember what are some strategies for once you've gotten it all on one side? Because there's more than one method for solving a quadratic, right? There's more than one way to do it. Can you think of some ways that you've solved quadratics in the past? Factoring. Factoring is one way. What's another way?
Quadratic equation.
Quadratic equation, that's another way. What's a third way? Completing the square, yes. So we have three basic ways, two of which we normally use. We don't often use completing the square, but sometimes. And another way that we'll see in a second is sometimes we have these nice easy quadratics where it's something squared equals a constant. In those cases, we can take the square root of both sides. Sometimes that's a strategy as well, depending on the setup, of course. So in this case, is this one factorable? Because we know some quadratic equations are factorable, but some aren't, right? So is this one right here that we're looking at, x squared minus x minus 20, factorable? And how do we know? Yep, x minus 5 times x plus 4. So we're looking for a factor pair of negative 20, right? That because it's going to have opposite signs, we're looking for a difference of 1, and 4 and 5 certainly fit that description. And because the middle term, after we FOIL this out, needs to end up being negative 1, we want the larger one to be negative 5, right? Or sorry, the negative 1 to be 5, and the positive 1 needs to be 4. And so by factoring it, what was the point of factoring it? Why is that useful?
Set that parts equal 0.
Yeah, because if something times something equals 0, then one of those two somethings has to be 0, right? So that means either x minus 5 had to be equal to 0, or x plus 4 equaled 0. I mean, the two possible values that x could be would be 5 and negative 4, right? So often we use set notation. We say x is equal to, and it's sort of going off the side of the page there, but x is equal to the set of 5 and negative 4, because there's a set of two numbers that are possible solutions to that equation. Okay? So that's for the most basic types of quadratic equations. We can just go right ahead and we can use factoring like that, right? Now, in some cases, unfortunately, equations, and in many cases, I should say, quadratics are not factorable. In fact, there's many more quadratic equations that aren't factorable than there are that actually are factorable. So if you can factor it, it's nice. And factoring is still useful, even though it's not always possible to factor a quadratic. And the reason it's useful is because it's always faster, pretty much, than any of the other methods. Right? So if we can factor, we still like to do that. Now, on the other hand, some of them are not factorable. So, all right, so not all factorable quadratics are as simple as the ones we had before. In any case where we have a quadratic equation where a is equal to 1, the coefficient on the quadratic term is equal to 1, it's just a matter of finding a factor pair of c, right, that either has a sum or a difference of the middle term. It's very basic and straightforward. Now, on the other hand, if a is not equal to 1, it ends up being a little bit more difficult. Not terribly difficult, but certainly a little more difficult. So, for instance, if I had the equation 2x squared plus 5x minus 3 is equal to 0. Okay. In this instance right here, a is not equal to 1, and so we have to not only consider factor pairs of 3 to help us get the 5 middle term, we also have to look at the first term as well. Did Mrs. Little this year talk to you about using the fishbowl method for these types? Okay, so in the fishbowl method, we realized that the coefficients on the x terms in our binomials are going to contribute to this 5x as much as the factors of 3 are going to contribute to the 5x. So we have to sort of put all this together and figure out what the inner and the outer products are going to give us to figure out if 5 is actually going to work. So the way we organize all those factor pairs is we take all the factor pairs of 2x squared here, or just 2. We can forget about the x because we know it's always going to be x and x, right? And just look at all the factor pairs of 2. So 1 and 2. And 2 and 1 are only the only factor pairs of 2. And we want to list all the factor pairs in both orders for this first one. It's important to check all possible combinations that we have them in both orders. And then we're going to look at all the factor pairs of 3, which just 1 and 3, right? Now, since 3 here is negative, right, that means that the factors of 3 have to be opposite signs, right? And in that case, when we're foiling this out, the inner and the outer products are going to have opposite signs. And so we're looking for an inner and outer product that have a difference of 5 as a result, right? And so we only have 2 possible combinations. Either we have 1x and 2x, and then 1 and 3 for our second terms in our binomials. And so if we multiply those together, right, the 2 multiplies the 3 in that case, the 1 multiplies the 1, and so we get 6 and 1, right? And then we can put the x on that if you want to think of it as 6x and 1x, and that has a difference of 5, right? So that's a good combination. Right away we have one that works. 3 and 1 and 2 and 1 and 1 and 3 wouldn't work because we'd have a difference of only 1 there. We need a difference of 5. So we're going to go ahead and set that up, right? And so that if we picked 1 and 2, that means the first one is 1x and the second one is 2x. And if we picked 1 and 3, the 3 has to multiply the 2. So does the 3 have to go on the left or the right? If the 3 has to multiply the 2 in that FOIL situation there. Left, yep. And then the 1, of course, then has to go on the right. Which one needs to be negative and which one needs to be positive to give us a difference of positive 5x? Which one should be negative and which one should be positive? The 3 or the 1? 1 should be negative, right? Because that's going to be negative 1 times x is negative 1x, and 3 times 2 is 6x. 6x minus 1x would be 5x. So, yeah, right ahead. That's got to be positive. So, we factor it out now, and we're going to finish up using the same strategy we did before. We know that if a times b equals 0, that either a or b has to equal 0. So that means, in this case, x plus 3 has to equal 0, or 2x minus 1 has to equal 0, right? So x has to equal negative 3, or I'll get 2x equals 1, so x equals 1/2. So those are my 2 possible solutions, negative 3 or 1/2 here. So it's a slightly more complex process. You have to consider more factor pairs, but if you use the fishbowl method, it's still pretty straightforward, right? Any questions about that before we move on? All right. We also know that quadratic formula is more often than not something that we do have to use because there are many that are not factorable. So if I have an unfactorable, what's another word for unfactorable? An unfactorable polynomial. What's an unfactorable number? A number that only has 1 in itself as factors. What? Prime, yeah. So we say the same thing we call unfactorable quadratics, prime quadratics if they're not factorable. well, what do we do with those? We use the old quadratic formula, which says that for any quadratic, x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Hopefully you did the derivation of that in Algebra 2 this year. Not going to worry about that. As long as you know it and know how to use it, that's the important point. And so quadratic formula is universal, right? Any quadratic, whether it's factorable or not, you can use quadratic formula. Once again, factoring is still preferable if it's possible because it is faster, but quadratic formula can be used all the time. All right, so for instance, how about you guys go ahead, let me pick one that's going to have something that we're going to have to simplify. I don't have it in there today. Let's take a guess here. Why don't you guys go ahead and solve the following quadratic using quadratic formula? Okay, go ahead and solve that using quadratic formula. Make sure any radicals or roots that you end up with are fully reduced, and make sure the fraction that the quadratic formula gives you is also itself fully reduced. A lot of times with quadratic formula, the devil's in the details, and reducing it properly is the difficult part. First thing you want to do is what?
All the terms on one side.
Yep. So I'm just, whoops. I am going to go ahead and put them all on the left side here, which just involves putting them on the right side and then just switching the sides of the equation here. And so do we have a factor pair of 4? We actually do have a factor pair of 4. There's a difference of 3. But I asked you to use quadratic formulas. Let's go ahead and use quadratic formula. But also we should acknowledge it is factorable, and if I didn't ask you to use quadratic formula, you'd probably want to solve this one by factoring because it'd be faster. But let's go ahead and make sure we get the same. What solutions are we going to get by factoring? What are the factor pairs of 4 that have a difference of 3?
4 and 1.
Yeah, negative 4 and 1, meaning my solutions would be positive 4 and negative 1, right? So if we don't get positive 4 and negative 1 from our quadratic formula, we know we screwed up along the way, right? So we'll get negative b. B in this case is negative 3, right? So negative b is going to be positive 3. Plus or minus the square root of b squared, that's going to be 9, minus 4 times a, which is 1, times c, which is negative 4. All over 2a. A is just 1, so it's just going to be 2 in the bottom there. So the first thing we should always do with quadratic formula is fully simplify what's on the inside of the square root. So 9 minus 4 times negative 4. What order do I have to do that operation in?
Multiplication first.
Yeah, you got to do PEMDAS, right? Multiply first. So negative 4 times negative 4 is
16.
positive 16. So really what this is the same as 9 plus 16, right? Those negatives go away entirely. So 9 plus 16 is 25. Okay, and so that's reducible, square root of 25, which is, of course, that's an easy one, 5. And so if we end up getting rational solutions, i.e. there are no square roots left over, 3 plus or minus 5 over 2, we want to write out each of those separately. So 3 plus 5 is, divided by 2 is, so 4 is one solution. And if it was 3 minus 5, it'd be,
2 over 2.
yeah, negative 2 over 2, which is negative 1, right? So we got the same solutions that we knew we would get from factoring, so that's a good thing, right? So the key is to always fully reduce your radicals and fractions with quadratic formula. So that is more or less it, though sometimes we know we get screwy answers, right? And by screwy, I mean we end up with situations where we have numbers that are not real numbers, right? Which, sorry, I'm trying to find some examples of what I'm talking about. Oh, there we go. So let's review complex numbers really quickly here. But sometimes, because of what A, B, and C are, b squared minus 4ac, right? So let's go ahead and start new. Right? Sometimes that whole b squared minus 4ac part, which is on the inside of the square root, in the case that we just saw, it was greater than 0, right? But sometimes it ends up being less than 0. And in that case, we end up getting the square root of a negative number, right? And what type of number do we call the square root of a negative number? Complex or imaginary, yep. And so the solutions end up being complex solutions. What's the name for that b squared minus 4ac part? A special name.
Determinant?
Yep, the determinant. Sorry, not determinant.
Oh, no.
That's a different thing. The discriminant.
Oh, discriminant.
Yeah, close, very close. And they actually sort of serve the same purposes in a lot of ways. So that's the discriminant, and if that's positive, we know that we have two real solutions, right? What if the discriminant's 0? What does that tell us? The square root of 0, can that be more than one thing? No, so even if we have plus or minus the square root of 0, it's still just 0. And so that means that there's only one possible solution. Real solution, right, but only one possible solution in the case of the discriminant being equal to 0. And if it's less than 0, then we have complex solutions, which means we should talk quickly about complex numbers, right? So, the square root of negative 1 is a special name. We call that I, right? And any number can be written, any square root of a negative number can be written as a factor of I, right? And we'd like to do that in all those cases. So, for instance, if I had the square root of like negative, let's see, the square root of negative 24. And I wanted to write that in terms of I, and also I'd like to fully reduce my square root. So, first of all, what do I do about that negative in front of the 24 immediately? Yeah, we're going to call this I square root of 24, right? And then 24, what's the biggest perfect square factor of 24? 4. Okay, so the square root of 4 is 2, so that means the 2 can come on the outside. And what do I have left over on the inside? 6. So 2I squared of 6. Right? And there's still stuff left on the inside of the square root that can't come out, so it just stays there. And the order that we always put these in is the numerical, the integer coefficient, 2, should always come first, followed by your I, followed by whatever's left in the square root. That's always the order that we write in. So 2I squared of 6 there. And so any complex number can be written in the form A plus BI, so it's a sum. A complex number really is considered, the way that we define it. Actually, I'm jumping ahead of myself really quickly here. Instead of doing that, what happens when I take I and I multiply it by itself? So I squared, what is that equal to? Because that's the square root of negative 1 squared. And the thing about it is this is actually a definition. It's not, because we can think of it in two ways, right? Square root of negative 1 times square root of negative 1. Well, what if you took the square root of negative 1 times negative 1, you got the square root of 1, and that would just be positive 1, right? But you could also look at that and say, well, it undoes the square root, therefore it has to be negative 1. And we go with the latter, that it has to be negative 1, because it turns out if I multiply two square roots together and they both have negatives on the inside of them, I can't use the multiplication rule for square roots anymore. So that's why it ends up being negative 1. All right, so I squared is negative 1. So anytime I multiply I by itself, we got to make sure that we just end up with negative 1. That's about all we need to know as far as the basics of I and how its mechanics work. We need to be able to reduce negative square roots by writing them in terms of I. We also need to know that I squared is negative 1. That's pretty much all you got to know about I. But in general, for complex numbers, right, with complex numbers, right, really, the I part is what we call the imaginary part, right? With complex numbers, it's the sum of a real number, which we'll call A, and the complex part, which is just BI, so some real number times whatever I happens to be. And so we have the real and the complex part of the number. And you guys probably talked about the complex plane and the absolute value of a complex number at one point during the year. We're not going to really worry about that so much now. We might revisit that later. It's not as important. But just knowing what a complex number is, the sum of a real number and an imaginary, sorry, that shouldn't say complex, I should say imaginary. It's the sum of a real number and an imaginary number. Imaginary because, of course, the idea of a square root of a negative number doesn't really lead to anything sort of concrete in the real world. And so we know that some quadratic equations are going to lead to imaginary or complex solutions. And that's sort of why this is important. But before we get to that, let's talk about just some basic arithmetic with complex numbers. So then by arithmetic, I mean multiplying, dividing, adding, and subtracting them. So arithmetic with complex numbers. So for instance, if I had, let's say, two plus 3i minus 4 minus 7i. So if I'm subtracting or adding complex numbers, what do I do? And what do you remember about that? When I'm adding or subtracting complex numbers, how do I handle that?
Variable.
What?
It's like a variable, so
Yeah, you treat I like a variable, exactly. So if it was the same as if you had like 2 plus 3x minus 4 minus 7x. So what do we have to be careful of with this subtraction operation here?
the negative.
Got to get distributed to both terms, right? So we have 2 minus 4 for the real part, right? So we add the real parts together, those are like terms, right? And we add the imaginary parts together, those are like terms. So 2 minus 4 gives me negative 2 for my real part. And 3i minus negative 7i, what's that going to leave us with?
10i.
Plus 10i, yeah. So adding and subtracting complex numbers is very straightforward. All it is combining like terms. Multiplying, it's a matter of foiling, right? I think you probably remember most of this stuff. So if I have to, instead of adding or subtracting, what if I went ahead and I had to multiply? Right? So go ahead and multiply those out. You're going to have to FOIL those, right? And make sure you remember the fact that I times I is negative 1. And then see if you can't remember what to do with the following. So anytime I'm dividing two complex numbers, what do I like to do with those? See if you can dredge it out of your memory, because we definitely cover that in Algebra 2. So take a crack at both of those. Good. That's a good one. All right. This first one here, we're going to FOIL it, right? So first outer and last, let's go ahead and multiply it first. So first will give me 2. Outer, 2 times negative 7i will be negative 14i. Inner, negative 3i. And last, so negative 3 times negative 7 is positive 21, right? But I times I is negative 1, so you have a third negative sort of in there. So it's going to end up being negative 21, right? That's an often made mistake that people get plus 21 because they forget that the I times I also throws in an extra negative sign there. And then once we FOIL, it's just a matter of combining like terms. 2 minus 21 is negative 19. Negative 14 minus 3, negative 17. All right, and we always put the real term first and the imaginary term second. Now, does anyone remember what I do when I have an imaginary number, a complex number divided by another complex number? How do I take that and make it so I don't end up having a complex number in the denominator?
Multiply by the complex conjugate?
Yeah, we multiply the top and the bottom by the complex conjugate, which would of the denominator, right? Which would be what in this case?
2 minus I.
Yep, 2 minus I. So the top and the bottom get multiplied by 2 minus I, and that's going to eliminate the imaginary part of the denominator. So the process of dividing complex numbers is really just the process of making the denominator not imaginary. We just want it to be a fraction that doesn't involve a denominator that's an imaginary number. Because it's really hard to think about, well, what does that mean, right? Because if we put it, if we do this process of multiplying the top and the bottom by the complex conjugate, we'll end up getting a complex number in A plus BI form, which is really what we want all of our complex numbers in. So really another way of putting it is dividing complex numbers is just a matter of transforming them into their A plus BI form. All right, so let's go ahead and FOIL the top and the bottom. So the top will get 6 for first. Outer will give me negative 3i. Inner, negative 2i. And last, negative I times negative I it's a lot of negatives. Negative 1. We have 3 negatives, right? Right, because negative I times negative I, the negative times the negative is positive, but then I times I is negative 1, so it's going to be negative 1. So there's a lot of negatives flying around there. First, for the one on the bottom is 4. Outer, negative 2i. Inner, positive 2i. And last is going to be negative 1, right? Positive 1. Positive I times negative I is always positive 1. Now, the reason that the I goes away is because anytime I multiply conjugates together, and conjugates are 2 binomials, the only difference between them being the sign in the middle, right? Anytime I multiply 2 conjugates together, the middle terms always go away, right? That's no matter whether we have complex conjugates or real conjugates, any type of conjugates. And the middle terms in this case are always going to contain our imaginary parts, which in this case, because they go away, no more imaginary numbers in the denominator, right? So we'll end up with, on top, 5 minus 5i. On bottom, 5, right? So how can we simplify this fraction?
1 minus 5.
Yeah, we can break this up as, what we can do is we can factor the 5 out of the top, actually, is probably the best way to do that. And then we realize the 5's cancel. We can only simplify a fraction if the numerator is factored, right? And we just get 1 minus I. And that is the A plus BI form of that number, 3 minus I over 2 plus I. So dividing is just a matter of getting it into A plus BI form, which is a matter of using the complex conjugate to eliminate the imaginary number in the denominator. So it's just some mechanical stuff. Not so bad. All right, so we just got done talking about imaginary numbers and complex numbers, and the whole utility of that is that sometimes we end up getting imaginary solutions to quadratic equations, and we'll talk about the significance of that in a little bit. But first, I just want you to go ahead and solve the following quadratic equation, and you're going to end up with an imaginary number as your solution. So here it is, 4x squared minus 6x plus 5 is equal to x plus 1. So this is one that is not currently in general form, so you're going to want to put it in general form first, and then use quadratic formula. To solve this quadratic equation here, first thing we're going to do, of course, is get everything on one side, put it in standard form, or general form, rather. Right? right? So if I subtract the x and subtract the 1, I'll end up with that. And now we're going to plug it into quadratic formula. X equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And so we'll get 7 plus or minus. Now 49 minus 4 times 4 times 4, what's that?
64,
So 49 minus 64 is what?
negative 15.
Negative 15. All right, so we have an imaginary solution, square root of a negative number. We want to write this in terms of I, though, right? So what can I do with that square root of negative 15?
I squared is 15.
Yep, so 7 plus or minus I square root of 15. Now, if the square root of 15 were reducible, we would reduce it, but it's not, right? And so, is there anything else we can do with this?
Yeah.
No, just going to leave it as is. And that's it. Now, we'll talk about the graphical significance of that in just a second. But before we get to that, I want to look at one other type of quadratic that we can use a different strategy to solve. For instance, what am I looking for here? Sometimes I don't need to use factoring or quadratic equation. There's an even faster method for specific types of quadratics. Now, whoops, that doesn't look good. In a situation like this, what do you think would be an even faster method than using quadratic formula or factoring? Because if I wanted to either do factoring or quadratic formula, I'd have to FOIL out that x plus 4 times x plus 4, and then distribute the 3, and then get everything all on one side and combine all my like terms. That'd be a pretty time-consuming process, right? What's an even faster way than doing that, just because of the way this is set up with the x plus 4 squared part right there? Try and be clever. Think of a clever way to do this that's not going to involve using quadratic formula or factoring. And I'll give you a hint. If you remember completing the square, this is one of the steps of completing the square. It ends up involving a binomial squared, right? What do we think? Any ideas?
Divide 3 out.
Divide the 3 off, yep. That's a good start. Now what can I do? Yeah, take the square root of both sides. That gets rid of that x plus 4 squared, right? And we'll just be left with x plus 4. When I take the square root of both sides of an equation, what type of square root do I have to take? There's a special type of square root that has to end up happening here. Can I take just the positive or just the negative one, or do I need both? Both, because we know quadratic should have two solutions, right? And that's where the plus minus comes from in quadratic formula. So plus or minus square root of 8 over 3. And the last thing we can do is just subtract the 4 from both sides. Now that square root of 8 over 3, that doesn't look so great. What should we do with that? That's not what we would call a fully rationalized or simplified radical, right? What can we do to simplify that square root of 8 over 3 there?
Square root of 8 over square root of 3. That can get 1.
Okay, so we have square root of 3 in the denominator. What does that mean? We want to get that out of there, don't we?
Multiply by square root of 3.
Yeah, multiply the top and the bottom by square root of 3 to rationalize the denominator. Plus or minus square root of 24. 3. And then square root of 24, that can be reduced, right? What is square root of 24 reduced to?
2 square root of 6.
All right, and we would actually like this to always be one fraction. So how can we combine this into a single fraction? We have to have common denominators, right? How can I make negative 4 have a denominator of 3? How many thirds is 4? 12 thirds, yeah. So this is going to end up being negative 12 plus or minus 2 square root of 6 over 3. That's the form that we would always like to have our final answer in. Just like that looks just like quadratic formula, right? And that's what our answer should always look like. Okay, so the simplifying part is admittedly a little bit time consuming, but imagine if I just wanted a decimal answer, I didn't care about like an exact answer, then this would be a lot faster because I could just stop after or at this step right here, and just plug it into the calculator to get the decimal approximation. Of course, if I have the calculator, chances are I can use the root finder, which is what we're going to talk about next. Okay, so in solving all these equations, we've solved linear equations, we've solved quadratic equations now, and it turns out that there's a major unifying concept that's involved with all of these types of equations that we're going to get our calculator in on in a second here. So, what that is, the idea of the roots of an equation, right? These relate to the x-intercepts of the function. And we'll see how they do in a second here. Right, so let's say I have an equation, and so if we're going to start talking about functions again here. Let's say I have the function, rather, y is equal to f of x. Right? And f of x can be anything. It could be a quadratic function, like x squared plus 2x minus 3. It could be linear, like y equals 2x minus 2, just a linear function, right? Now, if we take that function f of x, and instead of having it equal y, set it equal to 0, make y equal to 0, right? What does that correspond to on the graph of the function? Let's say, here's my function right here, right? This is my function f of x, and that's the graph of the function f of y is equal to f of x. Y, once again, it could be a quadratic, linear, polynomial, higher order, whatever. What does f of x equal to 0 correspond to? When y is equal to 0, where on the graph of this function are we? Because we're at the x, so those are the x-intercepts, right? Happens here, 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 and here. All right. And I sort of just threw that f of x there. F of x is just a fancy way of saying y, right? But it's also a fancy way of saying there's some function, some formula that is f of x that equals y, and that's your function right there. So it's a function of x. So an example of this is, an example of this in action would be, let's go to the next one here. Quadratic function y is equal to 2x squared plus 3x minus 9. No idea what this is going to... And what we're going to do here is we're going to go ahead and graph this. So you need a calculator? You can just borrow mine because I'm going to graph it on the thing. So we're going to go ahead and graph this using a graphing utility, and then we will draw what it looks like. The graph of this function, as we saw by looking at our graphing program, looks something like this, right? And so we can see that we have 2 x-intercepts here, right? We have 2 x-intercepts. Right, and so it turns out those x-intercepts correspond to the solutions of the equation 0 equals 2x squared plus 3x minus 9. All right? And so what we're seeing here is that if we take that function and set it equal to 0, right, we're going to get this equation, and the solutions to that equation are going to be the x-intercepts of the function that we're dealing with, this function right here. Right? And so we're going to use this concept to solve equations using our calculator. So our calculator is really good at finding x-intercepts of functions. That's the one thing the calculator is really good at. So what we're going to go ahead and do right now is to solve this equation. Instead of using quadratic formula, which we could, or factoring if it's factorable, I'm not sure if it is, probably isn't. But instead of doing it that way, we're going to find the x-intercepts of the graph of this function, right, with our calculator, and that's going to be the same as the solutions to this equation. And we're doing this for a quadratic function, but can you see how this is going to be a universal concept that's going to apply to any function, whether y is equal to 2x squared plus 3x minus 9, or whether y is equal to 2x plus 3, or whether y is equal to like log of 5x minus 4, or any other crazy function that you can think of. We can solve, if we set that equal to 0, the solution of that equation is going to be the x-intercepts of that function. And so we can use that idea to solve equations like this. So we can start with this, find the x-intercepts of this, and then we have the solutions of this. So how are we going to do that with the calculator? Let's go ahead and do that right now. So Using our graphing utility, whether it's our graphing calculator or I use my the Desmos utility here on the iPad, I found that the x-intercepts, the two x-intercepts of this function were -3 and 1.5, and those correspond to the solutions of this equation. So what the takeaway to this is, anytime I have an equation, if I take the equation, put everything on one side, set it equal to 0, and then whatever is on one side, not the 0 side, but the other side, if I go ahead and make that equal to y in my calculator, make that a function, y equals whatever that function is, whoops, not sure where that came from. Whatever y ends up equaling, whether it's a quadratic like this one, or it could be linear, it could be any other type of function, any type of function at all. Once I plug that in for y, and I find the x-intercepts, I found where it's equal to 0, right, because that's where the x-intercepts occur, and that will be the solutions to the equation that I'm looking for. So we can find the x-intercepts of the corresponding function to solve the equation graphically with our calculator, and that is universal for any type of functions. This is a very powerful idea. All right, so I'm going to give you some examples right now that you're going to go ahead and solve using your calculator in this method. Okay. And these might be equations that you wouldn't be able to solve any other way currently because you don't have any other way of doing it. Okay, so for instance, go ahead and solve the following equations graphically, please. So that one. And the next one. And then an even crazier looking one. Whoops, this one should be equals 0. And then the next one. And the last one there, that's a weird equation that involves a trigonometric function and a logarithmic function, something you have never solved before, but it doesn't matter because this strategy with your calculator works for any type of equation. You're going to get everything on one side, plug it in for y equals, and find the x-intercepts, and that will be the solutions to the equation. All right, so give that a try. First thing you're going to want to do is, in each case, if it already isn't already on one side, get it all on one side. So this first one will be x squared minus 4x plus 4 equals 0. And then this is what we'll plug into our y equals, and we'll find the x-intercepts of y equals this, and that will give us the solutions of this equation. This one's already set equal to 0, so I don't have to do anything with it. And this one, same deal, let's get it on one side, so it doesn't matter what side, in this case, minus sine 2x equals 0. Okay, so we've gotten everything on one side. Now we're going to set this equal to y equals, this equal to y equals, and this equal to y equals in our graphing utility and use it to find the x-intercepts. So we'll go one at a time here. So with this the first two, you can already see x equals 2, x equals 0.84. And the last one here, we got lots of solutions. We got 1.485. We got 3.424. We got 6.773, and I don't have any room to write them, so I'm just going to do 2 ... there, but we also got 7.331 and 10.2, so there was a total of 6 solutions for that. Whoop, and also 4.365, I didn't mention that one. So there's 6 possible solutions to that equation. Very interesting. All right, so that's how we can use graphing to solve any type of equation. Linear, quadratic, weird logarithmic, trigonometric combination like this last one, doesn't matter. You can solve equations graphically by finding the x-intercept of the function when you put everything on one side, set it equal to 0, and then plug it in for y equals, right? Another strategy that works equally as well, and sometimes it's easier, in some cases it's easier, in some cases it's actually more difficult, but looking at the last equation, log x equals sine of 2x, In fact, I'm just going to make it log x equals sine x, just to make it a little bit easier here. The equation log x equals sine x, there's another way we could possibly solve this. Instead of getting it all on one side and thinking of it as the solution of the equation as the x-intercepts of that function, what we can do is treat the two sides of the equations like two separate functions. So the function y equals log x and the function y equals sine x. And log x equals sine x when they intersect, right? So the solutions of that equation are the intersection points of these two functions. Right? So we can go ahead and graph this function and this function separately, and then we're going to use the intersection feature of our calculator, which I'll describe in a second, to find the intersection points of these two functions, which will be the solutions of that equation. So that's another way we can graphically solve equations, by finding the intersection of the two functions. So what you're going to do is go ahead and graph both of these, and you'll do second calc intersection, and you're just going to choose the two functions, and once again, it's going to ask you for one function, and the next function, you're going to use your cursors to choose the two functions by hitting enter once you've selected them. And then you are going to scroll your cursor as close to the intersection point that you want, there might be more than one, and hit enter for a third time, and it will give you the x value of that intersection point, and that's one of the solutions. And repeat that method for all of the intersection points, which will be all of the solutions to that particular equation. So if you're successful at using the intersection function to solve these two equations, you should get x equals 2.696, 7.328, and lastly, 8.264. All right. Now, same worksheet as last night. You're going to do numbers 15, 40, 41, 42. I should just say 40 to 42 all, I suppose. 44, 45. 47, 49, 51, 52 and 53, and then 55 through 58 all, 77 through 80 all, and lastly 82. So that'll be the homework for tonight. I will email that out to you for the people who weren't here today especially. So that's it. So same worksheet, nothing new. And tomorrow we're going to finish up the last part of our Algebra 2 review. And then on Thursday we'll get going on real pre-cal topics.